I created an alternative for you. So I created my own chatbot that will help you through your math problems. You can get to it a few different ways, and I'll show you how it works. You can get to it through my webpage, right there, Math Chatbot. You also can get to it through Alex. Right on the side of every one of your questions now will be a little instructor resources, and there's my AI chatbot. My suggestion to you is it works a lot better if you have it on your phone. So if you go to the webpage on your phone, it works a lot better because you can literally take pictures of your work and send it right to it, and it'll look at that work. It's a little harder on the computer screen because you got to copy and paste things to and then import it in, but it's actually a nice little thing. So here's how this works. So the first problem we're going to do tonight is this problem. So I'm just going to upload it. And it goes. Now watch, it's going to break on me. It will not give you the answer. Okay? It is literally going to give you guiding questions just like I would in class to go through and do it. So it's like, okay, what's the first step you try? Well, try plugging the number in. So if you plug the number into this problem, you end up getting 0 over 0. See? This is awesome. What happens when you get 0 over 0? And it literally walks you through it. So if you're totally and utterly stuck at it, you can do that. Now, say, okay, so I plugged that in. Now watch, I'm going to send something else to it. So you've done some work, and you're like, okay, I plugged it in. I simplified it down, and I got to this point. So it looks at your work and says, oh, that's what you've done. So that's what I'm saying. If you do it on your phone, you literally can take pictures of your work on paper. It will look at it for you. And you're like, nope, can't be factored any further. And it'll just keep going. It is another resource for you. Totally free, totally on my website, integrated into Alex and everything else for you. I figured this might be a little better than the Alex explanations because at least it's working with the problem that you're struggling with and not just a random number problem that they gave you in the explanations. Okay? So just another resource for you. All right. Now let's go back to this problem. Because I know how much you all loved limits, I decided to bring it back. So what's the first thing we're supposed to do with limits? We plug it in. And if you plug in 2 to this, you're going to get 0 over 0. What did I tell you about a problem that comes out to be 0 over 0? If it comes out to be 0 over 0, that means what can you do? It is a removable discontinuity, which means I should be able to factor those numbers out of it. So I can factor out a t minus 2 from both of these. Okay. If you don't remember how to factor, that's okay. That was, remember, we did, you can do synthetic division for this to pull it out. So synthetic division, we'll write it down. Bring this down to -6 to 0. We do it to the bottom. And they both should come out to be 0. So then I have what I just posted there a minute ago. You get t squared minus 6t plus 9 over t squared minus 4t plus 4. And then we do the limit as t goes to 2. If you plug it into that, what do you get? Oh, so close. Although the funny part about it is when I did it first, when I was playing around with my chatbot, I put 1 over 4 too. The middle is negative 8. So you have 4 minus 8 minus plus 4 is 0. So this comes out to be 1 over 0. Okay, so if I get my limit as going to 1 over 0, so what does that mean that limit's going to go to? What's 1 over 0? Because remember, we plugged in a number, so it's not really 0 on the bottom. It's getting really, really close to 0. So it's going towards infinity. The question is it going to positive infinity or negative infinity? Okay. I need to close this. So we need to figure out if it's going to positive or negative infinity. So the top's obviously positive, it's just 1. The bottom is t minus 2. So as we're getting closer and closer to that, it's squared. That's also going to be positive. So it's going to positive infinity. That works really, really well when I have something that I can actually factor things out and solve things for. But what if we get something like this? What's the limit as x goes to 1 of ln of x over x minus 1? Same concept. Plug your number into it. What is ln of 1? That is 0. And 1 minus 1 is 0. So now I have 0 over 0. I can't factor. Is there any algebra that I could do to possibly simplify this down? Anybody can think of anything I could do to simplify this down? I don't have an equal sign, so I can't do something to both sides. If I multiply the top and bottom by something, it might make my life a little bit easier, but the top's still going to end up being 0. So we have to have another rule, another process. And this process is known as L'Hopital's rule. So he's French. It's pronounced L'Hopital, not L'Hospital. It's just spelled hospital. I remember when I was writing the calculus book, we spent about a month trying to determine the proper spelling of his name because there's been multiple ways to spell his name. So what this says is if the limit of f of x and g of x so goes to 0, or they go to infinity. So on the top and the bottom, they either go to 0 over 0 or infinity over infinity. Then we can take the derivative of the top and the bottom and find the limit. And it will give me the exact same answer. Okay, it'll give me the same limit of the original function. So we figured out that we could do the derivative of the top and the bottom, not the derivative of the entire function, derivative of the top and the derivative of the bottom separately. So we're not going to use the quotient rule. And based on that, that limit will still give me the same limit of my original function. All right, so let's go back to this problem. This problem is 0 over 0. So it meets the criteria for it. So what's the limit, or what's the derivative? So if f of x is ln of x, what's f prime of x? What's the derivative of ln of x? 1 over x. What's the derivative of x minus 1? Just 1. So the limit as x goes to 1 of ln of x over x minus 1 equals the limit as x goes to 1 of 1 over x over 1.
The limit is the 0.
Correct. Infinity over infinity.
Then the limit of the function's derivative is the same as the limit of the function.
The limit of the numerator over the limit of the, or sorry, the derivative of the numerator over the derivative of the denominator. When you do the limit, it works. It's not the derivative of ln of x over x minus 1. Because if you remember when we did the quotient rule, we would have had to do f prime, that whole thing. We're not doing that. You're looking at them as two separate, unique, individual things. The derivative of the top over the derivative of the bottom. Find the limit of that one. It still gives you the exact same limit as the original problem. Okay. So plug 1 into this problem. What do you get? 1. So this one goes to 1. Okay. Here's my screen. This is this. All right. So you always have to plug in the number. All right. Because if the criteria is not met by it going out to be 0 or infinity over infinity, you cannot do this problem. Well, L'Hopital's rule does not work. So for this one does come out to be 0 over 0. But if I was to change this to cosine, it wouldn't. Now it'd be 1 over 0. And L'Hopital's rule doesn't work. Okay? It has to be 0 over 0 or negative or infinity over infinity. All right, so this one, if I plugged in 2, I get 4 minus 4 sine of 0 is 0. 2 minus 2 is 0. All right, so now find me my derivative of the top and the bottom. What's the derivative sign of x squared minus 4? How do we do this one? Tell me the answer. We'll go from there. Remember, don't forget the chain rule. Okay, you have to do the chain rule for this one because there's something inside of the sign. That's where that 2x came from. And then sine goes to become cosine, so it's cosine of x squared minus 4. What's the derivative of x minus 2? Just 1. So now I'm looking at the limit as x goes to 2 of 2x cosine x squared minus 4 over 1. So that becomes what? Just 4. Just 2 times 2 is 4. Cosine of 0 is 1. Here, arc sine rule. Because I doubt most of you remember that one off the top of your head. All right, so this one does not come out as nice and clean as the other ones. I'm gonna move this one over here. So if you plug in 0 to this, what do you get? We still get 0, right? If we plug 0 into this, we still get 0. And if we plug in 0 to the G, we still get 0. Correct? Okay. That means I got to do it again. If you get 0 over 0 still, the rule still works. Take the next derivative. See if it cleans it up enough that you can find it again. I do not like this problem. This is not a nice problem.
What was it? Second derivative equal -16x 4x squared. So,
What was it?
just plus on how you got your derivative for that second time around.
So the 4 is gone. I'm not even worrying about that one. Oh, actually, it's a plus because that's a negative. I'm going to take care of that one. So it's -4 times -1/2, which is +2, times the middle to -3/2. And the derivative of the inside is -32x.
Then why it went from 1 line.
Oh, I just distributed the 4x squared. So because it's not 1 minus, it's just that 4x squared. So I just changed the 4x squared to 16x squared. Okay. Yeah, I made my life a little easier. Yeah. You can do it as, I can simplify that down. So yeah. I'd be able to get rid of that x. Oh, actually, in that case, it actually doesn't work out to be 0. So I can actually get rid of that and that. So you can actually, okay. That makes my life a little bit easier in this one. So we get -64. over 20x to the third, 1 minus 16x squared. Good call. So this ends up going to negative 64 over 0. Which means it goes to negative infinity. Good call. I missed the X on the top and bottom. I was going to say, this topic literally said do L'Hopital's rule twice. I'm like, I wasn't expecting to have to do it 3 times. Yeah. Oh, wait. No. Oh, yeah. Actually, you're right. That should have been a 3. You are correct. But that actually works there, too. You still have to cancel it out. So look for ways, even without that screw up, it still would have, you still would have had to cancel out the X in there. So look for ways to simplify it algebraically at every point. You should only have to do those twice. Technically, you can do L'Hopital's rule as many times as you want. So like if you did this one again, the X would have vanished on the top. Even doing it one more time would have solved the X problem either way. It's just messier. There it is. I want one that's not an arc sign, maybe. Yeah, we can do this one. This one's fine. All right, try this one. All right, so plug in the 0, we get 1 minus 0 minus 1. So 0 over 0. Always plug in first. All right, so we've got four e to the 4x minus 4 plus 2 sine 2x over 2x. If you plug in 0, what do we get? What's the top come out to be? What's 4e to the 4x? What's 4e to the 0? E to the 0 is 1. 4 times that is 4. So 4 minus 4 is 0. What's sine of 0 is 0. So we still get 0 over 0. So take your derivative again. (16 plus 4). Huh? Because that's still 1. So 16 plus 1 is 16. Cosine of 0 is 1. 4 times 1 is 4. So 16 plus 4 is 20 over 2. So the answer is 10. All right. What's different about this one? Huh? It is a pi. It's not going to 0. What else? And that's a what? That means a what? Huh? Yeah, it's just a one-side limit. The rules don't change. The rules still stay the same. Okay. You still, if it's 0 over 0, you can still do the L'Hopital rule and stuff like that. So the rules do not change for this one. What's the limit? What'd you get? Yep. Okay. Don't forget to plug in your numbers. Because if you actually did L'Hopital's rule on this, you'll get the wrong answer. Okay? Because if you did it, you'd have ended up getting cosine of x over sine of x. So cosine of x, this goes to 1, actually negative 1. And that goes to 0. So that would actually go to negative infinity. They do not come out to be the same. Okay? So L'Hopital's rule only works when you have 0 over 0 or infinity over infinity. No other time does it work. Look at that later and wonder why that's wrong. All right, we have other indeterminate forms. These are all the different types of indeterminate forms. 0 over 0 and infinity over infinity, we've already talked about. What's if you think about it, 0 times infinity. You would think, okay, that equals 0. The problem is when we're looking at doing limits, which one gets there first? Because remember, we're not talking about it as at that exact point. We're talking about as it gets to there. So if it's getting to 0 faster than it's getting to infinity, the answer would be 0. If it's getting to infinity faster than it's getting to 0, then the answer would be infinity. That's what makes it an indeterminate form. Okay. So L'Hopital's rule also works on these. But we have to have our problem in terms of a fraction. If it's not in terms of a fraction, we can't use L'Hopital's rule. So we need to be able to work to be able to change things so that they come out to be fractions. So you know what? I'm doing the different one first. Hold on. This one first. All right. So what's if you plug in 0, x is going to be 0, right? What's ln of 0? What happens as ln is getting closer and closer to 0? So if we look at, because you might not have looked at the actual graph of ln of x in a while. So if we look at, here's the graph of ln of x. As it's getting closer and closer to 0, it's going to negative infinity. So this problem, as we plug, if we plug in 0, we have 0 times negative infinity, which is an indeterminate form. So how can I rewrite this so I have this as a fraction? You cannot take the derivative before it's a fraction. So how can we use algebra to rewrite this problem? Because this is going to be the hardest part of this topic. Huh? Okay, but what's the derivative of 1? Huh? It's 0.
Power of x.
If you put,
ln x to the power of x.
well, then I have 0 to the 0 power, which is also actually an indeterminate factor. So, but that technically, you could do that. That is an algebraic way. That's right, but it's just not going to help me solve this problem. I need it as a fraction. Yeah. Yeah. So there was actually a question on your test like that. That I think I had one of them. It was like it was over x to the negative second power, and you just had to bring it back up. So if I rewrote this as ln of x over x to the negative first power, or ln of x over 1 over x, that's the same thing, right? Okay, I now have a fraction. Is it still indeterminate? Ln of x is going to infinity. 1 over x is going to infinity. So now it's infinity over infinity. Still indeterminate. Now, but now I have a fraction. I can do L'Hopital's rule. So yeah.
Didn't set it up as the numerator and denominator. This tries to help.
It will not work. It will not work. There are situations where the answer will come out to be the same, but that is purely by coincidence. So I have 1 over x over 1 over x squared, or negative 1 over x squared. So that is negative x squared over x, which is negative x. Which that limit, as x goes to 0, it doesn't make a difference from which direction at this point, is 0. The reason that plus the coming from the right side has to be there is because ln of x doesn't exist on the other side of 0. This is the first one we think we've done that has infinity. If we plug in infinity to this, what do we get? So the x goes to infinity, right? What's the sign of 4 pi over x go to? What's 4 pi over infinity? And goes all the way to, we're doing the limit, it's going to what? 0. So what's the sign of 0?
Your input appears to be a jumble of words.
Yeah. Because you shouldn't have been listening to me. So it goes to what? Sine of 0 is 0. So this is pi times 0. Again, indeterminate. Okay. Now, this one's very similar to the last one. I just have an x in front. So I can change it to the 1 over x. So I can change this to sine of 4 pi over x divided by x to the negative first power. So let me see where I got that. Keep change flip for your divisions. Or if you left them as x to the negative second, you can just cancel them out. All right. So can I do the limit of this one? So 4 pi over x is still going to 0, right? What's cosine of 0? Cosine of 0 is 1. What's 1 times 4 pi? It's 4 pi. Is it not going to give me one? So these two, easy. This one, change to a fraction first. So the next one is infinity minus infinity. You might think, okay, why? 0. Again, same concept as 0 times infinity. Which one's getting there faster? Okay. Notice what's missing from this list. If you have infinity minus infinity, wouldn't you expect to have infinity plus infinity? Maybe. But that one, it doesn't matter because it's going to infinity. Because it doesn't matter which one gets there first. Infinity plus infinity doesn't cancel out. Infinity minus infinity gives you that 0. So that one actually matters, the direction. So we look at one like this. We have a subtraction problem. Whenever you have a subtraction problem, if we plug in a 0 to this, we still get infinity minus infinity. Because 5 over 0 is infinity, and 5 over sine of or 0 is again infinity. So we need to put these fractions or these things together. We cannot take the derivative of each one independently. So find a common denominator, put them together. Once it's one fraction, then we can do L'Hopital's rule. So x sine x, that's a product. So we have to use the product rule. We plug in 0, what do we get? We get 0 over 0. So we got to do, and there's nothing I can do to simplify that the way that it's written. So L'Hopital's rule again. So see if this works. We plug in 0, we get 0 on the top. 1, 2, 2. And anticlimactically, it comes out to be 0. The first couple times I taught Calc 1, I didn't teach the L'Hopital's rule until I taught Calc 2 and realized how important the L'Hopital's rule is to Calc 2. And I'm like, oh, yeah, really need to teach that part. Because when you do chapter 11 in Calc 2, which is all the series problems, you do limits a lot. And the L'Hopital's rule really comes into play in that section. Try this one. E to the infinity is infinity minus infinity. So infinity minus infinity is, yes, indeterminate. So how do we want to rewrite this one so it's a fraction?
So that it would be a fraction.
What was it?
But x to the power of negative.
So yeah, chances to
Or that there's simplified.
well, it would simplify the same thing. The question is does it?
Wouldn't it be e to the x minus 1 over x?
Yeah. I still need the x to a negative 1 up here. What if I did this? Can I do that? Yeah, multiply and divided by the same thing, right? Okay. So now I have x, e to the x over x minus 1. Right? Okay. What's x go to? Go to infinity, right? And then e to the infinity is infinity over infinity minus 1. Okay. So the question is as this is getting infinitely large in here, and that's infinitely large, but now I have a product, which is fine. I no longer have a subtraction. I have a product. That goes to infinity. It's no longer indeterminate. So sometimes when you're playing with these, this is why we claim pre-calc is probably the hardest and most important class. You learn how to manipulate things. And when you can manipulate things and understand like the things you can do algebraically to a problem, you can make your problem easier to work with. All right, so let's see. We've done the first 4. We now have these 1 to infinity, infinity to 0, and 0 to the 0. You might think 0 to 0 is 1. It's not. It's undefined or indeterminate. So let's look at a problem like this. All right. So if we do this, if we plug in 0, we get 1, and cotangent of 0 goes to infinity. So 1 to the infinite power. So we're kind of stuck in that respect. What's the annoying piece of this problem? I cotangent x in the x bar. Because I have 1 to the infinite power. Or 1 to any power is 1. Yeah. So, but that's the problem. It's like, but the bottom really isn't 1, it's going to 1. Because 1 to any power is going to be 1, but did it get there to 1 first or infinity first? That's the piece. That's what makes it indeterminate. Because we're not just plugging numbers in. If we're just plugging numbers in, the answer would be 1. Okay, because it's 1 to any power is going to be 1. However, since we're going to that point, we're taking the limit as we're getting close to that point. If that bottom of the base isn't 1, if it's anything else, and the infinity got there first, it's going to infinity. Or it's going to 0, depending on which side of 1 it's on. So that's what makes it indeterminate, because we're not exactly sure which direction it's going. It could be 1, it could be 0, it could be infinity. We don't know. So that exponent was causing me the trouble. Do we have a way to get things out of the exponent? It is. That's the only way that we can get things out of the exponent is a natural log or a log, right? I'm going to use ln, it's less letters. So we actually end up rewriting this problem. And we're going to take the L, because we can't take the ln of one side without offsetting it. So by having it as y equals, we can take the ln of both sides. So I have ln of y equals, and now that cotangent of x can come down. Cotangent of x ln 1 plus sine 4x. I don't remember. I have to look it up. But we're going to actually change this in a second anyway. Remember, whenever I'm doing L'Hopital's rule, I want with fractions, right? So if I have the limit as x goes to 0 of ln of y equals the limit as x goes to 0 of ln of 1 plus sine 4x over tangent of x. All right, so now that I have that, if I plugged in 0, I still have 0 over 0. So now I can do L'Hopital's rule. So my top piece is 1 plus, wait, no, sorry, 4 cosine of 4x over 1 plus sine of 4x. And my bottom is secant squared of x. Secant squared of x, plug in 0, you get 1. Sine 4x or sine 4 of 0 is 0. Cosine of 4x or cosine of 0 is 1. So this whole thing comes out to be 4. So I have the limit as x goes to 0 of ln of y is 4. There's got to be a reason I kept writing it. I didn't need to write it. I would have wrote it 4 times. So no, we're not done. So what I found was the limit as x goes to 0 of ln of y. I have to undo what I did at the beginning. So how do I get rid of the ln? What do I got to raise both sides to get rid of the ln? E. E and ln's cancel each other out. So if I did the E of both sides, now that's gone. So that becomes the limit as x goes to 0 plus of y equals e to the 4th, which is 9. So we put it in the beginning. We have to undo that ln at the end to find my final answer. And remember, at the very beginning when I started the problem, y was just that whole thing there. So the limit of y is the limit of the original problem. All right, one more. All right, so this is 0 to the 0 power, right? Yes. How do we want to adjust this problem? Yeah.
That we did Excel.
Oh. So if we did the limit, so what was x ln of x? Where we did that one? Right, but what was the answer? 0. One of the beautiful things is you've already done it. Don't do it again. 0. And then we have to do the e to both sides. So the limit as, actually, I'll just write it up here. Ends up just going to e to the 0, which is what? Yeah.
You just said we've already done it. Want to test your like exam if we run into that situation, we still don't do it again, just take it to the previous problem. Or do you want us to show our work again and get to it?
No, so if you had done, so like if the first problem, if I had a problem, like those two problems on the test, you can literally just write down, like you could have said this goes to that because you knew that already. You didn't need to show me out all the work to get to that point because you've already done that on the test. If you really want to make sure that I don't screw up and realize where it is, you can say, I did this in problem 4. That's fine. There's lots of things like that's actually one of the big things when you're looking at proofs. Once we proved it, you can use it again. Like, don't waste your time in going through and doing things again just to do things again. Now, you could have, if this problem was on the test and you didn't remember that you could do it, you could do it exactly the same way that we just did the last problem. We broke it out like this, and then you just do the x ln of x by changing that to ln of x over 1 over x and doing the same process. You could have still done it out. So, but since I literally did that problem early in class today, I'm not going to, we didn't necessarily have to redo it. This one was designed to make you see that you've actually done that piece based on the problem we did before. So, we've hit them all the indeterminate forms. And as you can see, the L'Hopital's rule, just like everything else, is not going to be the thing that's going to screw you up. Yeah. For your test, I will tell you which ones could be on there. But in the end, as I was just saying, that's not going to be your problem. Your problem is going to be taking it and doing the algebra to manipulate the problem to get to a point where you can do the L'Hopital's rule. That's going to be the piece that's going to screw you up.
So we should be able to do the outcome program.
Yeah, you should be able to do all the L'Hopital's topics now.
Like that.
Yeah. Yeah. And I don't think they're all actually in Alex. I think Alex only does a couple. Alex does 0 times infinity, infinity minus infinity, 0 over 0, and then applying it twice. I think those are the only ones that don't. I think there's only 3 topics that actually does it on it. So I don't think they don't do the other ones, but it is in the book and it does show up later on, so that's why I did them. But they're just not in Alex. So I did post all the videos from last week. Sorry, I forgot. They're up there now, though. And play with the chat bot. Have fun with it. If it doesn't help you, let me know. If it's great, let me know. If it screws something up, let me know. I'm playing with it and trying to make it better. So, but it won't give you the answer. Don't try. It will literally just say, I'm sorry, I understand it's frustrating, but I can't give you the answer. Have a good night. I'll see you Thursday. You can try. I actually had one of my students did it earlier today, and it got to the point where she goes, I think you need a human to help you with this.
I actually had a bit of trouble with it during class.